Hello, welcome back. Today we're going to go over an exercise where we're going to use the properties of definite integrals to find the values of the definite integrals provided in A, B, and C. And we are given certain definite integrals with their values. We're going to try to see how we can use these values to deduce for the values of these integrals. And here are certain properties of integrals. If you have two integrable functions f and g on a closed interval a and b, and if you have a constant k, you can define two different functions. One is k times f, constant times the f function, and f plus or minus g, the sum or difference of these two functions. And you can talk about the integrals of these brand new functions kf and f plus or minus g. In the first case, as you see, the integral of k times f of x dx from a to b is exactly the same as that constant k times the integral of f dx. So in other words, if you know the integral of f from a to b, all you're going to do is just multiply that by k, and that's the value of the integral of k times f of x dx. And same thing here, so integral of the difference or sum of these two functions is the sum or difference of those like individual integrals of f and g. So if you know those integrals, all you're gonna do here is to take the sum or difference of these values, and that would be the value of this integral. And I think there's one more property I want to mention here. If you have the f function to start with, and it's defined at x equals a, so the integral of f from a to the same a is going to be 0. Okay, so if you have the upper and lower limit exactly the same, that means that the integral of the function over that interval is going to be 0. So we're going to use this property for part A. All right, here we go. So for part A, we have the integral from 2 to 2 of x dx, but I just showed you that property. If the lower limit is equal to the upper limit, the value of this integral is exactly equal to 0. And regardless of the function here, the integral from the lower bound to the upper bound, where these bounds are the same, the integral is just 0. All right, for part B, we're going to use one property that if you have k times f of x, let's say from 2 to 6. In this case, k equals like 1/4 because that's the multiple of f of x, and f of x is x cubed, right? So in other words, this turns out to be 1/4 integral from 2 to 6 of x cubed dx. What is given in the question statement is the integral of x cubed dx from 2 to 6, and that's 320. So this integral is exactly equal to 320, and we get the 1/4 of that, so this integral is in fact 80. So the value of this integral, I go ahead and then write 80 here. And for the integral in C, we are going to use all the properties that I listed earlier. Why don't we use these two properties for part C? The two properties that I just mentioned can be used for this integral to split this into 3 integrals, in fact. So I'm going to write 3 integrals here. All of them are going to be from 2 to 6. All right. So the first one is going to be what? The integral of 2x cubed. But 2 can be pulled out all the time because it's a constant multiple. So this is integral of x cubed dx. And then this is a minus sign. And the coefficient of x is just 1. So, but in fact, it's minus 1. So I pulled it out. So this becomes just x dx. And the last term is a constant 6. Why don't we pull out 6 and just worry about the integral of dx? So all 3 integrals are provided us in the question statement. So in other words, this is 320. And this is 16. And this is just 4. So let's see what this adds up to. So let me just continue from here. So this integral is equal to 2 times 320, which is 640. Okay. And minus 16 plus 4 times 6, that is 24. So that is equal to 648. So we sort of like eliminated all the Riemann sums and limit business that we learned in the previous section to find the values of all three integrals, because some integrals are provided to us along the way. And that's the end of the video. Thanks for watching. I'll see you in another video. Bye.